Hi, it's Mr. T here, and today I'm going to go over Achievement Standard 91164. This is demonstrate understanding of bonding structure properties and energy changes. This is the the exam for this achievement standard from 2025. So we have three questions in the exam. The first question, I've shown the first 2 pages on the screen here, and we see that question 1 asks the following: sodium chloride, NaCl, is used as an antiseptic and antimicrobial agent. In analytical chemistry, it is often reacted with silver nitrate, as shown below. Now, these first 2 sentences are context. If we don't quite understand all the words they're talking about, it doesn't really matter. We don't need the first 2 sentences to answer the question. However, we do need to use this equation here, and we're going to use the next wee part to unpack. So we've got this equation shown that is sodium chloride plus silver nitrate goes to silver chloride plus sodium nitrate. Now, when silver nitrate, that's AgNO3, is added to 73 grams of sodium chloride. So notice they've given us the mass for sodium chloride. That's important. Sodium, 81.8 kilojoules of energy is released. Now calculate delta H for the above reaction, and then they've given us the molar mass of sodium chloride. So I've seen both of those bits of information, the mass and the molar mass of sodium chloride. So I'm going to expect that I'm going to use this data about sodium chloride to solve the problem. Now, the first thing I need to do is I need to calculate delta RH. Now, to calculate delta RH, I always ask my students to remember the following equation, and that is the energy that is given off or absorbed is equal to the enthalpy of reaction divided by the coefficient of the substance that we're looking at times the moles of the substance we're looking at. In this case, remember, we identified that the substance we're looking at is sodium chloride because it's 73 grams of sodium chloride. Now here, I want to work out delta RH, that's our unknown. We need to find out what the coefficient of sodium chloride is. So we go up to our equation and we find the term sodium chloride, NaCl, and we look and see what is the number in front of it. Now there is no number in front of it, so we take that as a 1. Sometimes there may be a 2 or 3, a 4 in front of there. We then go and find that for sodium chloride reacting, we are also given a Q value, or how much energy here is reacted, 81.8. What we're not given is we're not given the moles. Now this is quite interesting. We need to use this equation here because this is the only one with delta RH to find our final answer. We know 2 of the things, but we don't know the moles. However, we remember that we have this equation. We can calculate the moles if we take the mass divided by the molar mass. Now remember, they gave us the mass of sodium chloride. Here it is here, 73 grams. And they gave us the molar mass of sodium chloride. Here it is here, 58.4 grams. So I'm going to divide my 73 by 58.4, and I get the answer of 1.25 moles. So that's really important because now I found out the moles, the third missing piece of information I needed to solve this first equation. So I substitute in here my Q value, which is 81.8 kilojoules of energy. Notice it says is released, that is exothermic, so I'm going to place a negative in front of it. I don't know what delta RH is. Remember, I said my coefficient was 1, and I just calculated my moles as 1.25. So I've taken this equation and substituted everything in. Now here, all I need to do is rearrange and solve. Now some students that I have like to put it into an equation solver. I always would encourage people to solve this manually on their piece of paper, rearrange. But no matter which way you do it, it's the answer that's important. We end up with negative 81.1 divided by 1.25, which is an answer of negative 65.4 kilojoules per mole. Okay, now we know that the unit is going to be kilojoules per mole because we are calculating a delta RH value. So in this case here, what's going to happen if you got one of these steps correct, if you found out the moles correctly, or if you did this calculation correctly but had the moles wrong, you get an achieved. If you get the correct answer in the end, they give you a merit for this. Okay, the second question is here, identify which substances below match the information. So we are given 4 substances: zinc, ammonia, diamond, and sodium chloride. Okay, if we look at this zinc here, what we can go to this periodic table down the bottom, and we're going to see, is zinc a metal or a non-metal? And we can see that zinc is found here in the non-metals. Sorry, in the metals. What did I say non-metals for? So it's a metal. Zinc is a metal. We've got the metallic substance here, so zinc is going to be put in this part of the table. Let's look at the next one, ammonia. So ammonia is made up of nitrogen and hydrogen, and you can see that nitrogen is a non-metal and hydrogen is a non-metal. Now, because this substance is made up of only non-metals, and it's not carbon or silicon dioxide, then it must be a molecular substance. There it is, a molecular substance down here. That's our ammonia. Okay, the next one is diamond. It's carbon. Now we need to remember that diamond or silicon dioxide straight to covalent network. So the carbon here, we don't say it's a molecular substance because it's a non-metal, because carbon and silicon dioxide are exceptions. So we're going to place it up the top here. And then the last one we have is sodium chloride. Okay, so sodium chloride has sodium. Here, sodium is a metal and chloride is a non-metal. Whenever we have a metal and a non-metal in the same formula, it's a really high chance that it is ionic. So the sodium chloride is our ionic substance. That's cool. So using a skill that we've learned, we solve this table and they give us an achieved grade. Okay, so the next part of this question, relate the bonding and structure in ionic and molecular solids to the relative melting points. In your answers, describe the bonding and structure of ionic and molecular solids. Explain why the melting point of a solid indicates the strength of forces between its particles. Link the strength of forces between the particles. Okay, the use of strength of forces here is a really poor term for them to use, because you're not actually going to use the words force in this explanation. When they talk about strength of forces, they're talking about the strength of the attractions or the bonds that hold the particles together. And we're going to give it as in our example, we're going to take our 2 examples from the table. So we are looking at ionic, which is our sodium chloride, and our molecular, which is ammonia. So ammonia is a molecular solid, right? So we need to say what type of solid it is. Made up of discrete molecules. And here I've put NH3 molecules. These molecules, so we talk about the type of solid, the type of particles, the type of attractions. They are held together by weak intermolecular attractions. Then, once we've talked about this, if we're talking about melting point or boiling point, we're going to say, because the attractions are weak, only a small amount of energy. Really important you say small amount of energy. You can't say small amount of force. That's incorrect when we're talking about melting point and boiling point. This is why I said that the question kind of misleads us a bit. Therefore, a relative small amount of energy is required to break these weak attractions. Now, notice we use the word attractions instead of forces. Just use that all the time when you're talking about molecular substances, or if we're talking about stronger ones, we're probably going to use bonds. So because it needs a small amount of energy to break these weak attractions, its melting point is significantly lower. In contrast, when we talk about sodium chloride, it is an ionic solid. It has strong ionic bonds between the sodium and chloride ions. You could put between ions. Here I've been more specific and said alternating sodium and chloride ions. If you're not sure what the charge is of the particles, I'd always recommend you just give them their names, okay, and call them ions. Now, because of the strong ionic bonds, I should have said that here, but I said because of this, a large amount of energy is required to break the attractions and the melting point is high. And in this case, if you can recognize the relationship between the melting point and the forces between the substances, that is, if you said that molecular has a low melting point, then because it has weak attractions, you get achieved. If you said sodium chloride has strong ionic bonds because, it has high melting point because it has strong attractions, you get achieved. Or you identified that in order to melt, you have to break the attractions, that's an achieved as well. Or if you can describe the structure, that is the first two sentences, you get achieved. To get a merit, you need to describe the structure and bonding of one of these, or do one of these correctly, and link it to the energy required for melting. See, notice how I said we're not talking about force here, we're talking about energy, and we need that for merit. To get the excellence, you need to do both paragraphs correct. And so this gives us an opportunity to achieve merit and excellence. And notice on these first two pages, we've got 3 A's, 2 M's, and an E. Now, it's likely that in this first part of the paper, it's going to take 3 M's to get an M5 and 4 M's to get an M6. Okay, the next question. Looks like we're looking at substances again. Diamond, that's carbon, and gold, Au, are both used frequently in jewelry making, but their properties are very different. Diamond is very hard and can only be scratched by a substance equally as hard as itself. Gold, however, is malleable and ductile and used to craft intricate little small tiny shapes and patterns. Explain how the structure and bonding of each of these substances relate to the properties. Now, the whole first 2 sentences are just context, so you can go back and just ignore those and look. Diamond, see hardness. You're going to explain why diamond is hard. Now, as before, I said that we don't use energy to justify the high or low melt. Sorry, we do use energy to justify high and low melting points. We use force to justify softness and hardness. So in this case, we could say diamond is a covalent network where each carbon has 4 strong covalent bonds to adjacent carbons. As each carbon atom is was very strongly bonded to 4 other carbons in a tetrahedral shape, a large force is needed to break them, and hence diamond is very hard. So diamond is a 3D covalent network where each carbon has 4 strong covalent bonds to adjacent carbon atoms. As each atom has a very strong bond to 4 other carbons in a tetrahedral shape, a large force is needed. So large force, very hard. The first 2 sentences are always the same, or the first part, we always start with the type of substance, the type of particle, and the type of bonding. Okay, and we link those 3 together. That's always going to get us our achieve point for the start. On the other hand, gold is a metallic solid where each delocalized electrons, or where the delocalized electrons are attracted to the nuclei of gold atoms in, this is really important, non-directional metallic bonds. Non-directional, really important to say that when we're going to explain malleability or ductility. As forces push or pull the gold, the delocalized electrons allow the atoms to form new attractions as their old ones diminish. So the atoms can push past while diminishing their attractions to the electrons and forming new attractions to new electrons. This allows gold to be shaped without breaking. Now, if you recognize that the strength and bonding, or if you recognize in gold or diamond that the bonding influences the different properties, you get achieved. If you linked the bonding and structure of one of the solids to the properties, okay, so if you linked the bonding and the structure of, so if you did one of these correct, either the first one or the second one, you get a merit. And if you explain how the bonding in both results and the comparative properties, you get excellence. Sorry, if you do both of these paragraphs properly, you get excellence. So basically, you put down one good point you get achieved. You explain the paragraph for either of them. It's a merit. If you get both, it's an excellence. Okay, so the last question, we're going to expect this question in every paper, is we need to do a bond energy calculation. So in the development of the Haber-Bosch process, shown in the reaction below is the development of the Haber-Bosch process, shown in the reaction below, is historically significant. Nitrogen plus 3 hydrogens goes to 3 ammonia, and it produces energy, negative 93 kilojoules per mole. Calculate the average bond energy of the nitrogen bond, which is a nitrogen triple bond nitrogen, in N2 using the average bond energies listed. Now, in this type of question, they're always going to list the bond energies you need to carry out your calculation, and they're always going to draw the structure of the molecules so you can identify the bonds that have been formed or broken. Now, in this case, you can see there's an N triple bond N, and that of course comes from the N2 molecule. We can see that there's an H single bond H that comes from the H2 molecule, and we see this N with 3 bonds to separate hydrogens is the NH3 molecule. So we have to calculate the bond energy of N triple bond to N. So we don't expect to see the N triple bond N in the bond energy, because that is going to be the unknown, or X. We are going to, I always like to have a wee kind of table. We are going to take the bonds broken and we're going to subtract the bonds formed, and they're going to equal this answer here. We're going to do a algebraic equation. But in the first instance, just add up all of the bonds that are broken. And let's go through and see if we can do that. So the first bond that is broken is this nitrogen triple bond nitrogen. Now there is only one of them, and we don't know the value for it, so we call it X. So the amount of energy that is that we have here is just X, because we don't know what it is. The next bonds that are broken, that's the bonds on the left hand side of the periodic table. We have 3 H2s, so we can see that our H2 is an H to H bond, and we have 3 of them. Right, so we have 3 H to H bonds. So we can see the value for an H to H bond from the table here is 436. So we multiply this by 3 and we get 1308. So now we can see the total amount of energy to break the bonds is 1308 plus X. Remember, X is our unknown. Now we can calculate the total amount of energy to form the ammonia bonds. Now, in ammonia, there's only one type of bond. There's an N to H bond. There are 2 ammonias, and there are 3 N to H bonds in each ammonia. That gives us 6 of these bonds in total, 6 N to H bonds. Now the N to H bonds are 391 kilojoules per mole, so we end up with 2,346 once we've multiplied that by 6. That is the total amount of energy for the bonds formed. So this is great because we want to place this into this equation, that the enthalpy of the reaction equals the sum of all the bonds broken minus the sum of all the bonds formed. And we have the bonds broken on the left hand side here and the bonds formed on the right hand side. And we have delta RH given to us at the top. So we substitute these 3 values into our equation, and we get negative 93 equals 1,308 plus X minus 2,346. So we group all the terms, so the X is on the left hand side and all the numbers are on the right. So we get X equals negative 93 minus 1,308 plus 2,346. We solve, or sorry, we simplify on the right hand side, and we get x equals 945. Now you could, if you had substituted into the equation further up, you could put that into equation solver and it should give you the same answer. Now, in this case, we also have to give the unit. So we're going to say X equals 945 kilojoules per mole. Does that seem reasonable? Well, look, you've got these single bonds. They're in the 300 and 400s. So a triple nitrogen bond at 945 seems reasonable. It's going to take more energy to break this bond than it is the single bonds. So we're quite happy with this answer once we've checked it. We've got the correct unit because the bond unit is kilojoules per mole. Now, for this it says, did we correctly calculate the bonds broken or formed? So yes, if you got this answer 2346, or you got this answer 1308 plus X, you get the achieved mark. To get the merit, you have to get the correct process with a minor error. Now, a minor error could be you put a negative at the end. Now, these bond energies are always positive, so that would be wrong. A minor error could be that when you did this rearranging, instead of plus subtracting 93, you added 93. Or it could be that you didn't include the unit in the end answer. Okay, so to actually get an excellence, you have to have the correct answer with the unit. So the N to triple bond N bond enthalpy is 945 kilojoules per mole. And I just wrote that at the end because it asked me exactly what that was, so I stated it. So now we have, these are the last two, so we had 4 pages for this first questions, and we had 2 excellences available here. And it so happens that for this first whole question, if you get 3 of the excellences, you're E8. Amazing, fantastic, you did great. If you only get 2 of them, you're E7. If you get 3 of the 4 merits, okay, then you're at M6. If you get 2 of the merits, you're at M5. And if you get 4, 3, 2, 1 A's, you're at A4, A3, N2, and N1. Merits are quite good. Quite lucky to get the merit grade M6 with 3 merits. Look, we should always be aiming for at least M6s or E7s in these questions. E8 sometimes can be just you make a wee mistake in one of the words, you lose one of your E's here. So M6 though should always be your sort of bottom you're looking for, and then E7 or E8 if you're lucky. Okay, let's go on to the next question. Okay, question 2. Okay, so they've got a mixture here. They're looking at endothermic, exothermic. It says we can see them here. Identify whether each of the statements applied to endothermic or exothermic by circling. Okay, so the products have more energy. If they have more energy, they have absorbed energy, and they must be endothermic. Energy is released. Okay, exothermic. The enthalpy is positive. Well, we know that's endothermic. Cool. Well, that's quite straightforward. The next bit says, state whether the following process is endothermic or exothermic. Give your reason. Okay, we can see the process here is water gas going to water liquid. We know that water gas has no bonds between the gas particles, and water liquid does have bonds. So we have bonds forming. This process is exothermic. When H2O condenses to H2O liquid, new H2O to H2O bonds are formed. Bond forming is exothermic. So my explanation for this is we are making new water to water bonds. I put it clearly by putting the formula with a line between the next formula of the same thing. This is a good technique to get into because we're going to use this later when we talk about dissolving and solubility. So we form new H2O to H2O bonds, therefore it's exothermic, right? Because bond forming is exothermic. Okay, so the next bit down here is they've drawn the diagram. We expect that on most years we're going to have to draw it ourselves, but here, draw and label, they've actually drawn the diagram. So ammonium nitrate is used in first aid to treat injuries. The energy change in reaction is shown in the diagram below. It's actually used in cold packs. So if you have an injury and you break the cold pack and put it on your injury, it's the ammonium nitrate that's reacting with another substance that absorbs all the heat out of your injury. In this reaction, the graph above is the reaction in the graph above absorbing energy from the surroundings or releasing it. So we just have to say absorbing or releasing it. So in this case, right, it's starting at the bottom and it's going up to the top. It's got more energy, so it must have absorbed energy from the surroundings. Now, this is quite interesting. For this whole page here on the left, there's only one, there's an achieved grade if you do either of the three, well, you do any of the three things. So did you get 2 of these correct? Achieved. Did you say the energy was absorbed from the surroundings? Achieved. Did you say that this process is exothermic and that it's because the bonds are forming? Achieved. Okay, that's quite straightforward. You get a merit if you give a good reason for this part 2 here. So they gave a merit for doing the good reason. In fact, they gave an achieve for that as well. So I don't know how that worked out. But so for this whole page, you can only get an achieved and a merit. I think they kind of, when they wrote the paper, they weren't clearly thinking about how they were going to give the marks in this part. Okay, B, on the right-hand side here, we can see all of these compounds given the table below contain polar bonds. Yes, they do, right? We will talk about that, but only 2 of them are polar molecules. That's correct. Define what makes a chemical polar bond and give an example from one of the above compounds. Okay, so we could take any of them. We could take the carbon to oxygen bond here. We could go the oxygen to hydrogen bond here. We could go the carbon to chlorine bond here, or the oxygen to hydrogen bond. I'm just going to use the oxygen to hydrogen bond. It's a nice simple one for me. I give an example, let's say. So I'm going to say, but before I do that, I always use when I'm explaining about polarity U-back, but this is only half of the polarity explanation. So I'm going to use in the first part of U-back, which is EUB, okay, to explain this, but they want an example for a start. So I'm going to say OH is a polar bond. Correct. And the reason is because H and O have a difference in electronegativity. That's the U-back, the E part. So they share their bonding electrons unevenly. U from U-back, unevenly, producing a bond dipole. Now, in this case, a polar bond is a bond dipole. The polar bond is the actual thing that's created. The bond dipole is the negative and positive sides of the polar bond. Notice that we use polar bonds in some places and a bond dipole in the other, but it's probably okay to use bond dipole in most places when you're writing this explanation. So I talked about the U-back. The next bit it says is circle the compound above that is nonpolar. Let me think. Is there any here that are a symmetrical molecule? Well, methanol isn't. It's a tetrahedral shape, but one of the points coming off the tetrahedral is bonded to an oxygen when the other 3 are hydrogen, so it's not going to be symmetrical. It's asymmetric. Water, we know in our mind, even though they've drawn it like this, that this is actually a bent shape. It's derived from a base shape of tetrahedral. So this is asymmetric. And this one here, the tetrachloromethane, is actually tetrahedral, which is the symmetrical shape, and all of the atoms or the all of the bond dipoles coming off are identical, so it's going to have an identical arrangement of bond dipoles. So this is going to be a non-polar molecule. We have to explain that, and we're going to explain it using the rest of the U-back. So I'm going to start and explain that it does have polar bonds because I haven't talked about those first. As carbon, did they call that carbon tetrachloride, tetrachloromethane? I call that carbon tetrachloride, but hey, that's fine. It's got 2 different names. As CCl4 is a tetrahedral shape, the 4 polar carbon to chloride bonds are arranged asymmetrically. So these polar bonds are arranged asymmetrically. Now, when I talk about cancelling, I'm going to say it's the bond dipoles that cancel, not the polar bonds. The bond dipoles, those slightly negative and positive charges we assign to the polar bonds, they're the things that cancel out. So the bond dipoles cancel, and overall, the molecule is nonpolar. So it's tetrahedral, 4 polar carbon to chloride bonds arranged symmetrically. The bond dipoles cancel out overall, and the molecule is nonpolar. There we go. Okay, so for this one, they give us an achieved if we identify the symmetry of the molecule is responsible for the polarity. So we talk about, well, it's because it's asymmetric or symmetric. Or we identify the size of the dipole influences the polarity of the molecule. Well, that's interesting. If we link the symmetry of the molecule to the dipole cancellation using, okay, so if we do this bit at the bottom, they give us a merit. If we do all parts of 1, 2, 3 correctly, including the full explanation, they give us an excellence. Okay. They kind of ignore the first part. They give us the merit and achieved the merit for the first part, but then we get an excellence if we've done the first part correctly. So that's a kind of strange way of doing it, but is what it is. Let's go on to the next part of the paper. Okay, predict the solubility. This is historically, or it is a tricky question to explain. There are 2 ideas. There's the base idea that there are non-polar solvents and polar solvents. The non-polar solvents are this hexane here, and the polar solvents are water. Now, what we say is that non-polar substances dissolve in non-polar solvents. Polar solvent substances and ionic substances dissolve in water. So we look at the first one. We just looked at this carbon tetrachloride. Okay, we said that this was non-polar, so it's not going to be soluble in water. It's going to be insoluble. Now, the magnesium bromide, which is the ionic solid, it's soluble in water, but not in this non-polar hexane. So it's insoluble is correct. Now, bromine is a non-polar molecule, right? Because you've got 2 identical atoms and they share their electrons evenly, so they don't produce a bond dipole. You have a non-polar molecule, so it's in a non-polar solvent, so it is soluble. And if you put bromine, and you've seen it, it dissolves in hexane, it produces a purple color, nice sweet purple color. Okay, what makes sodium chloride soluble in water but iodine insoluble in water? And your answer refer to the structure and bonding of each substance, explain how the substance interacts with water, include a diagram for sodium chloride. Okay, let's start with iodine. Iodine is a molecular compound. Yay, okay. When placed in polar water, now here's where I talked about earlier in the paper that I used the water to iodine. I put a bond between these 2 molecules when the water to iodine attractions, when it's placed in water, the water to iodine attractions are weaker than the water to water attractions. Okay, so basically what we say is the water is attracted to water, and that's because they're both polar. It's actually more than that. They produce these things called hydrogen bonds, but we don't learn about that in this level. But water to water attractions are stronger than the water to iodine attractions. Because of this, the iodine will not dissolve in water. The water molecules basically form these strong attractions to each other and don't let any iodines come in between them. Okay, so that is the iodine. Explain why it doesn't dissolve. That's quite straightforward. We did give the type of substance. We say how it interacts with water, and we didn't need to include a diagram because that's for the other one. Okay. So sodium chloride is an ionic compound. Now, this is a tricky one to explain, but when placed in water, the partial negative oxygen, and we'll show this soon, in water molecules is attracted to the positive sodium. So a water molecule has a slight negative, that's delta negative on the oxygen and delta positive on the hydrogen. So the delta negative of the oxygen is attracted to the sodium ions, and the partially positive hydrogen atoms are attracted to negative chloride ions. So this is true. Okay. Now we have to link the next part. So we've talked about the structure of this. It's ions, right? And we talked about the attraction, but we have to say why it does this. The strength of this attractive force is strong enough to overcome the strength of the ionic bonds within the sodium chloride lattice, allowing the sodium chloride to dissolve. So what we're essentially saying is the overall attractions of the positive ions to the slightly negative oxygen and the negative ions to the slightly positive hydrogen are stronger than the attractions the ions have to each other within their lattice. We give an example of a sodium dissolving in water. Well, here is what we're talking about when we talk about the slightly negative water and the slightly positive hydrogen. And here's the example of it being dissolved. We have the water molecule surrounding the positive ion with their oxygen with the slightly negative adjacent to the sodium and forming these this attraction, which I show with the dotted lines. And we have the same thing for the chloride ion, apart from it is attracted to the slightly positive hydrogen. Make sure you just don't put a hydrogen with a plus. It isn't a full positive charge. It's a slight positive charge, and we use this delta positive to show that. Okay, and this is the end of question 2. And in question 2, there were only 2 excellence opportunities. You got an E8 if you got both of those right. If you made a slight mistake along the way, here maybe a slight mistake in your diagram, they might have said, well, you didn't quite get the E here, but we'll give you an E7 because it was only a small mistake. Again, they'll give you an M6 with 3 M's, an M5 with 2 M's, and then from 1 to 4 A's, they give you N1, N2, A3, and A4. That's 2 questions done, 1 more to go. Good luck if you're still watching this video. If you're getting a bit tired, have a break, come back to it later. Okay, next one, question 3. Okay, so carbon has different forms, allotropes, that have different electrical conductivity. Diamond does not conduct electricity, but graphite is a very good electrical conductor. You should have looked at the special example of graphite and how it is a 2-dimensional lattice and it has an extra valence electron. Okay, so it has these delocalized electrons. Compare and contrast the structure and bonding of these 2 carbon compounds. In your answer, explain the structure and bonding of diamond and graphite. Now, when they say explain the structure and bonding, we're talking about the type of substance, the type of particles, and the types of attraction. But in diamond and graphite, we have to be more specific. Is it 2D? Is it 3D? And we're going to talk about how many bonds there are that each carbon makes. We've defined whether it is electrical conductivity of solids and justify the difference in electrical conductivity between diamond and graphite. You may include a diagram to support your answer. I don't think it was necessary here. So diamond is a 3D covalent network where each carbon, this is important, each carbon has 4 covalent bonds to adjacent carbons. All 4 valence electrons are used in bonding, so there are no free electrons available to conduct charge. Now you might put in brackets here, there are no free charged particles. There are no other charged particles in here. There are no ions, so we're just talking about electrons in this case. However, graphite is a 2D conventional covalent network where each carbon has 3 strong covalent bonds to adjacent carbon atoms and produces a honeycomb lattice, right? This 2-dimensional, like a piece of paper. Remember that if they ask you the different types of questions, there are actually weak attractions between the separate layers of graphite. But we don't really need to say that in this question. Now, only 3 electrons are used in bonds, the fourth valence electron is free and is able to move and conduct charge. Now, they did say up there, define electrical conductivity in solids. So we should also have written here that in order for solids to conduct electricity, there must be a free moving charged particle. Okay, so we need to put that down as well, just to be sure. The answer should be fine, but to be sure, write that down. So 2D covalent network, 3 strong covalent bonds to each carbon. The fourth valence electron is free, and therefore it's able to conduct charge. Okay, so achieved here, if we describe the structure of diamond covalent network with tetrahedral arrangement or bonded to 4 other, so we did both. Okay, or describe the structure of graphite as network solid, each carbon bonded to 3 others, or we define the conductivity. For merit, explain bonding and structure of both carbon allotropes. So we did both, yeah. Or there's another merit, we link conductivity to the presence of the localized valence electrons in graphite to carry or lack of mobile charged particles to localize electrons. So it says here, as long as we put there were no free electrons or there is free electrons, we get the extra merit point. To get the excellence, we need to comprehensively explain the structure and bonding of both solids and relates this conductivity of diamond and solid. That's pretty much what we did by doing both of them. So well done to me, I guess. Okay. So the last, or the next bit of this question is they've got a couple calculations here. So let's go through this. Combustion is a chemical reaction where a substance combines with oxygen to produce heat. When ethanol combusts with oxygen, carbon dioxide and water are produced. Here's an equation. So this is a combustion equation. They've given us the enthalpy of the reaction, delta RH. It's negative 1,370 kilojoules per mole. Calculate the mass of ethanol. So we're using the same types of equations we used in our very first question of this paper. I don't know why they've put 2 more the same, but they did. So we've got 3 of these questions. We need to calculate the mass. They've given us the energy. They've given us delta RH. They've given us the molar mass. So we're going to use this equation to calculate the mass because we want to find the mass. They've given us, we don't know the moles, but we should better find that and using this equation here. So notice in this equation here, we want to find the moles. We know the coefficient because we've got the equation. We know the delta RH because it's up here. We know the energy released because they've given it to us here. So we know all 3 of these things. We can find out N, and then once we've found out N, we know what the molar mass is, but we'll go over that later. So I put all of these 3 things I've just said into this equation, the Q equals delta RH over coefficient times moles. And then I either put it in an equation solver or rearrange. Moles equals 17,050 divided by 1,370. I get moles equal 1.28 moles. It's actually 1.277, I think, but at this stage, I'm just going to write it to 3 significant figures, but keep the unrounded value in my calculator. So I'm going to take this value of moles and I'm going to plug it into this equation. So I rearrange this equation because I wanted to find out M, so I make it M equals N times molar mass. So N, of course, is 1.28, and the molar mass is up the top here. Put those in, and we get the answer is 34.1 grams. Well done to us. Okay, so we have to do the same type of calculation again using the same 2 equations. Calculate the energy change when we have 187 grams of zinc oxide. Oh, look, they've given us the molar mass. This one is actually more straightforward because I don't need to rearrange and I can start with one equation first and then go on to the next one. I don't sort of have to jump between. So what is the energy change? We know that we have the mass and the molar mass. Let's just find out the moles first. We know we're going to use the Q equals delta RH over coefficient times N because Q is energy change. So we don't have to write it down first. Let's just find the moles. The moles equals the mass, 187, divided by the molar mass, 81.4. So we get 187 divided by 81.4. That gives us 2.3 moles. Excellent. We know we're going to use this equation here, Q equals delta RH coefficient. Now in this case, the other two cases we've had in this paper, we've had the coefficient of 1, but in this case, the coefficient is actually going to be 2. And delta RH given to us, here it is, 696. And it's negative, so we just substitute these three values that we now have in, and we get Q equals negative 696 divided by 2 times 2.297. Now interestingly, it doesn't matter whether you do the multiplication first and division second, or the division first and the multiplication second, they still come out the same in your calculator, and the answer you get is negative 799 kilojoules. Now it's important here that the unit that you use for energy is kilojoules, but the unit that you use for the enthalpy of reaction is kilojoules per mole. So this is, now here it said calculate the energy change, so they didn't tell us that it was energy released or energy absorbed, so we have to make sure we put down the right sign, whether it's negative or positive. Okay, and here it was negative, remember, because our delta RH was negative. Now in this case, if you got one step correct in one of these equations, you got achieved. If you got the correct answer overall, that's 34.1 grams or negative 799 kilojoules for one of these questions, you got merit. And if you got it all correct, you got an excellence. Well done. Okay, let's have a look at the last part of this paper. The last part here is what usually they have in the past put at the front of the paper, but they've put it at the end just to mess with us, right? Okay, we're going to draw Lewis structures. So I've put a periodic table up there. Remember, you've got periodic table available to you. Hopefully you've just sketched in, or you've put a wee staircase just below the boron, above the aluminium. You draw a staircase and you identify what are the metals and what are the non-metals. Okay, so remember we use that when we're doing the types of substances. Okay, so we are looking first at carbon dioxide. So we're going to calculate how many valence electrons. So carbon is in group 14, so it has 4 valence electrons. And oxygen is in group 16, so it has 6 valence electrons. So we're going to add up the total number of valence electrons. So there are 4 electrons for one carbon, and 2 times 6, because there are 2 oxygens, electrons. That gives us 2 6s are 12 plus 4 is 16 electrons. We have 16 electrons to distribute. So the atom that goes in the middle is the one that has the most unpaired electrons. That is carbon. Always carbon goes in the middle, then nitrogen, then oxygen. They kind of like, carbon is the one, right? So we put carbon in the middle, the oxygen atoms around the outside, and we give them a bond each. There you go. First bond is free. Now we're going to put 8 electrons around each of the outside atoms. So oxygen already has 2. I'm going to give 2 more to make it 4, and then 2 more is 6, and then 2 more is 8. Excellent. Oxygen on the left-hand side has 8. Now, the right-hand side, oxygen has 2 from that bond, and then it has 2 more, 2 more, and 2 more. Oh, wait a minute. I have now used 16 electrons. That's them all used up. But my 2 outside atoms have 8 electrons, so I'm quite happy. But my center carbon atom only has 4. 2 electrons from each of the bond. So I'm going to have to move some of the electrons to make a double bond. So I move 2 electrons from the left and make a double bond, move them into the center to share them, move 2 from the right in the center to share them, and now the carbon in the middle has 8 electrons around it, and each of the oxygens have 8. So we have carbon dioxide that has 2 double bonds. And because around the central carbon atom there are 2 electron density regions that repel from maximum separation, we get angles of 180, and it's linear. Okay, so the next one, let's have a look at it. It is chlorine oxide. It has chlorine from group 17, that's 7 electrons, so 2 7s, and oxygen from group 16, that's 6. So we have a 6 plus 2 sevens is 20 electrons in total. We're going to put the oxygen in the middle because it's the one with the most unpaired electrons. And then we're going to put a chlorine on either side. We're going to put a bond between each. Remember, a bond is worth 2 electrons. And then give each outside atom 8 electrons first. There are chlorines. You'll get yours. And chlorine on the right, you get yours. I've used 16 electrons. I've got 4 left. The next 2 pairs go around the oxygen. Every atom is happy because every atom has 8 electrons around it. It fulfills the octet rule. So this is the final Lewis diagram. Or Lewis structure. The shape of this, there are 4 electron density regions around the oxygen. So that gives us angles of what, 109. They repel for maximum separation, and a base shape of tetrahedral. But remember, when we have only 2 bonds and 2 non-bonding in a tetrahedral shape, the overall shape is bent. Now this is always a tricky one because often we draw it and it looks linear, but we have to go through the process of explaining the shape in our mind, and then we remember and get the correct shape. Okay, so the last one is an exception. We see it's boron. Hey, boron. My teacher said something about boron. It said the boron only requires 6 electrons around it instead of 8. It's an exception. Okay, so boron trifluoride. There we go. Boron's in 13, fluoride's in 7. There, so that's 3 plus 3 sevens gives us 24 electrons. So we'll put boron in the center, okay, because it has the most unpaired electrons, 3. Fluorine just has 1 unpaired electron. Fluorine's around the outside. Give them each a bond each, and then give them their extra electrons, the outside atoms, just to make them happy. Now, in this case, we have used all our electrons. You might be tempted to make a double bond because the center atom only has 6 electrons. But then we go, oh no, we don't need to, because boron is actually only needs 6 electrons. So we've got the perfect Lewis diagram drawn already. Shape, well, 3 electron density regions around the middle, mutually repel for maximum separation. They produce angles of 120, which is trigonal planar shape. Now, because all regions are bonding, its final shape is also trigonal planar. And there we go. We did all of that work. And you know what? This year, they just gave us an achieved for all of this work. And that's the way that it goes. So let's see if we can answer the next question. I mean, sometimes they give you a merit if you do all of this correctly, but they didn't this year. So we go down to the next table, next part, and it says the table gives information related to the shape of each molecular substance. So we've got methane, its shape is tetrahedral, ammonia, its shape is trigonal pyramid, and they both have angles of 109.5. We need to compare the 2 shapes and explain the factors that contribute to the arrangement around the central atom and the molecular shape. I'm just going to straight go ahead and say you are going to use this Serasbo reasoning. You are going to talk about the central atom, the electron densities, regions, the repelling, the angle, the shape, the bonding regions, and the overall shape. I'll show you what I mean. So CH4 has 4 regions of electron density around its central atom. So I've talked about the central atom and electron density, first part. These regions repel for maximum separation, producing minimal repulsion and angles of 109. So I've done the repel and angles, and a base shape, a foundational shape of tetrahedral. I've talked about the base shape. So I've done the first 5 things. Seraz, amazing. Now I'm going to put in the next part, which is how many bonding, what's the overall shape. Okay. So as all the regions around the carbon are bonding, all the regions are bonding. I could have said all 4 regions are bonding, or 4 regions are bonding and no regions are bonding, but I was quite explicit here. I said all the regions. I talked about them being 4 of them above are bonding, so the overall shape is tetrahedral. Now remember, the reason that the base shape and the overall shape are the same is because we had all of the regions bonding. So I have talked about the arrangement around the central atom. Absolutely, that's this part, the second part, and the molecular shape, the last part. Okay, so let's do the same for ammonia. So ammonia also has 4 electron density regions around the central N atom repelling from maximum separation with angles of 109 and base shape of tetrahedral. So yeah, I've included all the same bits from the other. In fact, I could somehow combine this second and fourth paragraph together, but I didn't need to. And then finally I go, well, it's got 3 regions that are bonding and it's got 1 that is not bonding, so its overall shape is bent. Now, in this case, we got achieved for, we talked about the Lewis structure. So if you got 2 correct Lewis structures with their name, you got achieved. If you identified the correct number of bonding and non-bonding regions, or the correct number of, oh no, that's correct, then they gave you an achieved for this. If you recognize electron density regions that are arranged for maximum separation or minimum repulsion, they give you an achieved. If you linked the number of areas of electron density around the central atom and the lone pairs of the molecule shape for one compound, you got merit. So what they're saying is, did you say that there are 4 electron density regions that produce the angle of tetrahedral, but then said that there were 3 bonding and 1 non-bonding to make it overall trigonal pyramid. I don't know why I said this was bent before, trigonal pyramid shape for ammonia. Did you fully explain each substance, including the number of areas of electron density and number of lone pairs determine molecular shape? Yes, we did, but remember, we didn't call them lone pairs, we called them non-bonding regions, but they are the same thing, so you can get away with that. So, in the end here, you needed to get 3 excellences. That's quite a bit to get to the E8, 2 for E7, 3 merits for M6, 2 merits for M5, and then we've got 4, 3, 2, 1, 4 A's for A4, 3 A's for A3, 2 A's in 2, and 1 A is in 1. And finally, well, what are they going to give you overall? Well, actually, in this paper, you have to get 8 to get achieved. Sometimes it's 7. That's not very often, about 30% of the time. I would aim to make sure you get 8. The boundary for merit is 14. You need 14. It has been 13 in some papers, maybe at level 3 more than level 2. And to get excellence, you need 19. Sometimes that can be 20. Okay, so really aim to get as many of those E's as you can. I hope that this video helps you. Look, if it does, just give me some feedback and I'll make some more videos on this, on some chemistry, physics, or whatever you want me to. And good luck with your exams later in the year.